So we are going to be starting physics for today, which is Friday, May 15th. I told you this was going to kind of go fast, so we just kind of skim over several different, sorry, I'm doing my microphone here, several different topics with the chemistry. We'll definitely be spending a lot more time on acid-base balances as you get further into the program, along with physics too. So physics will be spending time talking about gas laws, density, airway pressures. So today's basically going to be some review, I'm thinking, hopefully. Of course, I know some people said they never took a physics class, but some of the first few slides here should be some kind of review of just general science, I guess. All right, so what is physics? Okay, physics is basically the study of the laws of matter and their reaction with energy. Okay, so remembering that matter is anything that takes up space and has mass. And this is where I was talking about this should be kind of like from a long time ago. There's three primary states of matter. We have solids, liquids, gases, and plasma. So plasma you may hear as being referred to as the fourth state of matter. However, for all intents and purposes of respiratory care, we're not going to be spending a lot of time talking about plasma. We're really going to be looking at spending most of our time really with gases. Alright, so this should be kind of some review from way back of general science of looking at solids. So when we think of a solid, we think of them having a fixed volume and shape. Okay, so their molecules have the shortest distance to travel between each other before they collide. Okay, the atoms found in solids are limited to the back and forth movement of the jiggle. So you really obviously can't see that with the naked eye, but there is some movement going on there. Solids maintain their shape by forces that are known as the van der Waals forces. Okay, so those are strong mutual attractive forces between atoms called the van der Waals forces. So as you go through this PowerPoint, again, terminology is big really in this class. I'm just kind of introducing or reviewing different terms. So I've tried to highlight those or bold them, basically, not highlight them, but bold them. So van der Waals forces, you're going to want to know that term. And there's two types of van der Waals forces. There's weak London dispersion forces, and then there's stronger dipole forces. Okay, so if you view this PowerPoint in a regular setting, you should be able to see the speaker notes and find a couple extra notes here. I didn't really add too much, but there's just a couple things. So that was two different kinds of van der Waals forces: the weak London dispersion forces and the stronger dipole forces. That's what kind of makes solids maintain their shape, hold their shape. All right, so liquids then, they have a fixed volume, but they adapt to the shape of their container. So whatever the liquid, whatever type of container the liquid's in, that is basically determines their shape. So if a liquid's not held in a container, then the shape, so if you like spill milk or water or whatever, then the shape is determined by different internal and external forces. And these liquids actually have weaker forces than solids, but stronger than gases. So the van der Waals forces kind of help keep them somewhat contained compared to gases. And liquids, one of the characteristics is they are not easily compressed. So all these characteristics you kind of want to know in comparison to each other. So gases then, they have to be contained, and they have very weak van der Waals forces. Therefore, they're able to move around a lot and collide with each other. They are easily compressed and expanded, and gases then exert a pressure. Okay, so as we ventilate patients, volume also, volume as in a gas volume, because when we talk about volumes or liters or whatever, or milliliters with tidal volumes, and a tidal volume is like your normal breath, depending on how healthy your lungs are, we actually record and monitor those pressures that certain volumes give. So you can imagine as you increase a volume, you're going to increase pressure, okay? And that's part of the gas laws that we'll cover in the next few days. All right, and then plasma is, again, the fourth state of matter. It's a combination of neutral atoms, free electrons, atomic nuclei. It can react to electromagnetic forces and flow freely like a gas or a liquid, but we're really not going to be spending any time on this as far as talking about it in our practice of respiratory care. So all this matter has internal energy, okay? So internal energy of matter. So the atoms that make up all matter are in constant motion at normal temperature, okay? So you think of all the atoms that make up the solid, liquid, or gas are in constant motion depending on what form that matter's in, okay? And there's two different types of energy. There's potential energy and kinetic energy. Two major types of this internal energy. So you want to know potential energy and kinetic energy and what they mean and what the differences are. So potential energy is basically energy of position, okay? So an example is an object that's balanced or sitting on a shelf. Okay, so most of the energy in solids and liquids are the potential energy. Okay, so it just kind of sits there. It makes up most of the energy in solids and liquids. And then kinetic energy is the energy of motion, like a falling object is an example. So if you think about gases, how they're usually more in motion, that makes up most of the gases' internal energy is kinetic energy. So when we're kind of comparing these different states of matter, we look at solids as having the highest potential energy. Okay, they're just sitting there, the higher energy of position. And then the lowest kinetic energy. Okay, so their chances of moving, I guess, are lower unless you push them or actually move them. Liquid then would have a higher potential energy than kinetic energy, okay? And then your gas then is going to have your lowest potential energy, the energy of position, and then your highest kinetic energy, okay? All right, so moving to the law of thermodynamics and what this means. So this is basically the science studying the properties of matter at various temperatures. Okay, so you think of how things kind of change depending on the temperature. Things behave differently depending on the temperature. So thermodynamics, if we kind of break up that word, we're looking at thermo meaning temperature, and the dynamics are the properties of temperature, how it behaves and how it relates to energy and work, and how different forms of energy can be transformed to one form or another. Okay, so work then, the term work can be viewed as a process of transferring energy to or from a system. So kind of with those other laws that we've talked about before, laws of conservation, I believe, and laws of, I can't remember, I have to look back. Energy cannot be created or destroyed. It can only be transferred or converted to one form to another. Okay, so it can't be broken down. We talked about that with like balancing equations. So it just kind of course, it can release energy on those types of things like ATP, but it's a law of thermodynamics, so have this term down. So now we'll be talking about the transfer, heat transfer. So the first law of thermodynamics tells us that the heat will move from a hotter object to a cooler object until the object's temperatures are equal. So that's established thermal equilibrium. So that makes sense. I mean, you take a hot pan or whatever out of the oven, it will eventually, with the law of thermodynamics, reach thermal equilibrium, where eventually the hotter pan will be close to what the room air temperature is as that heat disperses and kind of spreads out. Okay, so this basically then is an example of that transitioning from a higher state of energy to a lower state. Okay, so heat can be transferred in 4 different ways: conduction, convection, radiation, and then evaporation, condensation. So you'll need to know those 4 things: conduction, convection, radiation, evaporation, and condensation. We'll be spending a little bit of time on each of these in the upcoming slides here. So kind of again a little visual here, and I did type up the words. I know they're kind of blurry on this slide view, and they're actually been worse on a big overhead screen in the classroom. So I did put them as speaker notes on the bottom. So convection on the left, upper left. So that is the transfer of heat through a fluid, liquid or gas, caused by molecular motion. So you can see like the water is boiling there. And then conduction, that is the transfer of heat or electric current from one substance to another by direct contact. The transfer of heat or electric current from one substance to another by direct contact. Okay, so like the heat that's coming off of the flame heats the pan, and then therefore the handle becomes hot. Okay, so that would be the conduction. And then radiation then is the energy that is radiated or transmitted in the form of rays or waves or particles. Okay, so that's kind of like the radiating heat that would come off the pan, or the radiated heat that's coming off the flame, the fire. Okay, the pan meaning when you took it out of the oven. All right, so here are a little bit more definitions. So conduction then is the main method of heat transfer in solids via direct contact between molecules, keeping in mind that metals have the highest conductivity and gases have the lowest. So heat transfer between objects is quantified by using a measure called thermal conductivity. But I just mainly want you to know the main terms of conduction, convection, radiation, and then we'll be talking about evaporation, condensation. So then convection then is, when we look back at that other picture, was the one where the water was kind of boiling in the pan. So that's the mixing of fluid molecules at different temperatures. Transfers heat in liquids and gases. So an example of this would be forced air heating in your homes. So that's an example of convection. And I think there's convection ovens too that kind of have that idea. And then radiation then occurs really without any direct contact between 2 substances. It's basically the transfer of energy by photons and electromagnetic waves. So the sun's warming of the earth and radiant warmers would be examples of that. So there's really no direct contact. It's kind of traveled or transmitted by rays, waves, or particles. All right, evaporation, condensation, and vaporization. Okay, so again, these were like some old, I remember kind of learning this, I think in science, maybe like 6th grade or something. So vaporization is the change of state from liquid to a gas. So you're vaporizing it. Okay, vaporization is going to require heat, and this heat must come from surroundings. So you think about a vaporizer. I know when I was a kid, my mom used to use a vaporizer. I think now we're just humidifiers, but it actually was a, I'm dating myself, they're probably a huge fire hazard now. But it was basically a glass kind of jar-like thing that, oops, I think I accidentally was moving something on my computer to skip the screen, I'm sorry. So we'll come back to that. You have to look back at that, but let me just finish my little story. So this glass-like jar thing sat in this plastic kind of carrier, kind of plastic, basically protected the glass from burning or getting too hot, like on a tabletop, or on the, I think my mom actually put ours on the floor. And then there was this like heat unit, kind of like a stem kind of heat unit with a tube that sat inside the water. Of course, it plugged in, and that actually heated up the water, and it made steam. And then there was like this little medicine cup that you could put eucalyptus kind of oil, or Vicks. It was Vicks. I just remember some liquid Vicks stuff. And so it was something that you would use when you were had a cold or you're really stuffy. So that was the old vaporizers. They don't use them anymore, because I'm sure because they're a fire hazard. So that's why I always think of vaporizer kind of like that the liquid then changing to a gas, or even just if you're looking at a pan of water boiling. Okay. So then evaporation then is a form of vaporization where heat is taken from the air surrounding the liquid and then cooling the air. So an example of evaporation then is when we sweat. Okay, so the body uses this principle of evaporative cooling by producing sweat. So then the liquid sweat evaporates, and in that process the air helps cool the skin. Okay, so we think of our body as 98.6, and then a regular, of course depending on the heat of the day, but 72 degrees, we start to sweat for whatever reason, exercising, whatever. That's what helps cool the skin. And that's another reason why it's important to stay hydrated, because if you get dehydrated, you don't sweat, and then you're not going to cool yourself off. And then condensation is the opposite of evaporation. So this is where the gas becomes a liquid. And a good example of this is when you're camping and your exhaled gas then turns into a liquid or drops of moisture like inside the tent. So if you've ever been camping, that'll happen. Your exhaled air has a certain amount of water content in it, and then it forms droplets on the inside of the tent. Sorry, I bumped my slide. I can't for some reason go back on this. Alright, so now the next slide here is temperature. So temperature and kinetic energy are really closely related. So temperature is basically the measurement of the heat, and then heat is the result of the molecules bumping into each other. Gas temperature is directly proportional to its kinetic energy. In contrast, the temperature of solids and liquids represent only part of their total internal energy. Okay, so gas temperature is more directly proportional to its kinetic energy, where solids and liquids represent only part, that temperature represents only part of their total internal energy. So absolute zero, that's another term you just need to be familiar with as far as what it means. It's basically the lowest temperature that can actually ever be achieved. This happens when there is absolutely no kinetic energy, there's no movement going on, the molecules are no longer vibrating, and there's no heat that can be measured. Apparently researchers have come close to attaining absolute zero, but no one has actually ever achieved it. Okay, now this part here is going to go with these last few slides. Your homework then that will be due on Monday is just a temperature conversion worksheet, and there's two different documents that are under that temperature conversion homework. One is the actual worksheet itself, where you have to fill in the numbers, and then the other one is a sheet that kind of helps you with the conversions, gives you different formulas and things that you need to know to make those proper conversions. So when we look at the different temperature scales, mainly we're looking at Fahrenheit and Celsius. These are basically based on the properties of water, whether they're freezing and boiling. And then there's this third scale called the Kelvin scale, and that's based on molecular motion. So when we compare these three, you'll see the two here, and then the Kelvin is going to be on the next page. So your Fahrenheit is your non-metric, the one that we're most familiar with, and your melting and boiling points are whole numbers. When you're looking at Celsius, that's metric and centigrade. Oh my gosh, my tongue is tied today. Metric and centigrade. And there's 100 degrees difference between your freezing and your boiling points. And then Kelvin is represented by K, and it's basically an extension of Celsius scaled down to the absolute zero. And again, there's 100 degrees between freezing and boiling points. And just keeping in mind that your standard, your International System of Units, your SI, is a measure in Kelvin. So sometimes you'll see things in Kelvin. And then how do we convert those back and forth? So Kelvin's probably the easiest one. So with Kelvin, you have to just have your Celsius degree plus 273. So with that being said, when you're looking at your homework and you have to go from Fahrenheit to Kelvin, you're going to have to take another step. You're going to have to go from Fahrenheit to Celsius, then to Kelvin. Okay, because there's not a direct way to go from one to the other. You have to go from Fahrenheit to Celsius, then Kelvin. Once you're in Celsius, you can add the 273 and get to Kelvin. So then with going from Kelvin to Celsius, you're going to take your Kelvin temperature minus 273, and that's going to give you your Celsius. And then of course you'd have to convert back to Fahrenheit if that's what it's asking you to go from K to F. Alright, so you can choose which one you like to use. I know for your math exam, depending on which order you've done everything today, I did give you these equations. I did the one with the 1.8. I provided you with those because I know you're not going to remember them. I don't even remember them. I have to look them up. It's not very often that I have to convert Celsius to Fahrenheit. I mean, your hospital system usually decides on how you're going to measure temperature, body temperature, and then you just stick with that one way. So 37 degrees Celsius is 98.6 degrees Fahrenheit. So a 37 degree temperature in Celsius is normal. And you'll just get used to those numbers. I want to say for the most part, I want to say back in Wisconsin we did use Celsius, but as far as I've been here we've used Fahrenheit. So you choose which one you want to use, which conversion you feel more comfortable with. If you want to work with the decimals or the fractions, it's up to you as long as you get the right answer. And then this is a little diagram. This actually comes out of Egan's. And this is kind of looking at the three different temperatures and comparing them. So as you see, 0 degree Kelvin then is equivalent to negative 270 degrees Celsius, which then is equal to negative 460 degrees Fahrenheit. Okay, then if you move to 0 degrees Celsius, that is equal to 32 degrees Fahrenheit. Okay, so 0 degrees Celsius and 32 degrees Fahrenheit are freezing, which then is actually 270 degrees Kelvin. And then you have your comparison there of normal body temperature of 98.6, which is 37 degrees Celsius, 310 degrees Kelvin. I don't see any hospital systems using Kelvin. I think that's more like in the lab setting, like research. And then Celsius being 100 degrees, with Fahrenheit equal to 212, which is the boiling point, and then your Kelvin then is 373. So that is all I have for you today.